So we gotta just follow the train. So every one of them individually designed for that train. Now if one of them fall down and 15, 16 of them, fall down, guess what? We need to redesign all of that and rebuild it. So for a while, that line is out of order. So what we do, we switch the power to another transmission line. Now the problem that we have today, all of our transmission lines are over 100 years old. And they're over capacity, they're overloaded. So if something happened, we cannot send it on another line because that's already overloaded. And the way to control it is, if this line is overloaded and an extra power comes in, it will shut itself off. And then we'll send the power to another line. And before you know it, you have 4 or 5 grids all turn off. Some of you may remember about 15 years ago, 14 years ago, we had a 29 hours of blackout in New York and East Coast. Something happened in Cleveland, Ohio. A transformer blew up, high voltage, 500,000 volt transformer blew up. And the power automatically went another line. That line was, already overloaded. It shut it off, and the total of those two power went to another line. Before you knew it, this domino effect shut down, half of the grid system. For 29 hours, there was no power in the East Coast. And then President Bush came in and said, oh, we're going to spend $300 billion and fix these things. That was just a talk. We never spent a dime. We haven't spent a single penny in our infrastructure for the past 100 years. What we built at that time, at least I give them credit that they built it to take this capacity of today. But as we move forward, our need for power increases on a daily basis. Look at yourself. 15 years ago, there was no cell phone, no laptop computers. One of the things that you guys take for granted, Google. You just go and boom, hey, I have, I want to know whose dog. Google his name, see, what he knows. Instant. Google in just Southern California has 4 data centers. Each data center has more than 350 servers in it. And each data center uses 25 megawatt of power. So multiply that by 4 in Southern California. Multiply it by God knows how many all over the United States. See how much power goes there for you and I to get our smartphone out and just Google Dr. Toossi's name and find out that he teaches in Cal State Long Beach. Instant.
Nice work, Phil.
So, as you can see, our demand for electricity is going higher and higher on a daily basis. But we're not generating any power. We're not fixing any infrastructure. We're just keeping the old stuff going. So, the type of a transmission line, we have overhead and underground. 99.9% of our transmission lines are overhead because it costs 5 times more if we go underground. And the biggest problem we have, it's a concept we call it heat transfer. Because this power, when it goes underground, they generate a lot of heat. And we have to get rid of that heat, otherwise the cable underground will be melting and there won't be any power. That's why we use overhead, because, you know, the atmosphere, the air around it will keep it cool. That's why we have 99.9% of it, or not under. AC, or alternate current transmission, again, over 95% of our transmission is AC. However, about 25 years ago, Sweden came up, there was a company named ASEA, which today called ABB, ASEA Brown Boveri. They came up with the technology and they convert high voltage AC to DC for a long distance transmission. Reason for that, in the long distance transmission, we use somewhere between 7 to 12% of power for a long distance. We built a power plant at Delta, Utah for the city of Los Angeles. Bringing power 800 miles, we would have lost a lot of power through that line. That's one problem. Second problem is environmental issues. AC line in the wild, it will kill birds. And if anything happened, one of the transmission tower will fall and a car is under it or somebody's under it, guess what? They're going to get electrocuted. And also, there's a potential magnetic field that's created by high voltage power. So to get rid of all of that and make it cheaper to bring the power 800 miles, we convert the power from AC to DC through what we call converter station. We built one converter station in Delta, Utah, and then one converter station down here in Adelanto, right by Victoria, on the way to Vegas. So we converted 3,000 megawatts of power to DC, bring it to Adelanto, convert it back to AC, then send it to LA. And DC line, usually in a long distance, it's a maximum loss of 3%. So when you have 3,000 megawatts of power, if you lose 10% of it, that's a lot. 300 megawatts, it means enough power to basically provide power for the city of London. So you don't want to lose that. But, you know, losing only 3% is not that bad compared, to 10% and above. So that concept called HVDC, high voltage direct current, which is a converter station. I showed you a picture of it. And basically those are the, the AC system power loss and the DC system power loss through a long distance transmission line.
That one should be over a certain length, right?
Oh yeah, the farther you go, the more you lose.
So that 6.5% is over.
6.5%, it's over 1,200 miles.
Okay, 1,200.
Yeah. This is the converter station. The converter station has 2 valve halls. The interesting thing is that the concept that they use, it's a mechanical engineering concept. They use it in an electrical system to convert the power in a high voltage from AC to DC. Each valve hall has 3-phase going there, convert to 500,000 volt positive, 500,000 volt negative. So one line will come out of this, one line will come out of that, and that becomes a DC transmission line. Just 2 lines, positive, negative. And if you touch it, nothing's going to happen. But if you touch both of them, you'll be dead. If you touch one of them, you get a little shock. But